light source. And when you're trying to do image reconstruction, you always want a coherent light source. So the way they correct for this is that if this path had to travel a little bit faster, the straight one goes faster and the wiggly one takes longer, the mirror is deformable. And so you actually bend the mirror on the straight one down a little bit to make it an equivalent light path distance. So the mirror itself has all these little actuators. And it's actually made up of like thousands of little elements. Almost looks like a liquid mirror because they can manipulate it in kind of real time. And so they scan the atmosphere with a laser beam to tell what the deformations are in the atmosphere and then make the corrections to the mirror to account for it.
That's amazing.
So you could do something like this for the telescope, but it would be...
it's cheaper and easier to go above the atmosphere and just fly out.
I think so. It would be that's a very challenging thing to do. And normally when you do adaptive optics, as it's called, you're looking straight up. So or very close to straight up. If you look at the horizon, we basically never do astronomical observations on the horizon because you're looking through more atmosphere. Mm-hmm. If you go straight up, you're looking at the thinnest portion of atmosphere possible. But as you go closer and closer towards the horizon, you're increasing what we call the air mass, the amount of air you have to travel through. So here it's kind of the worst case because you're going through the entire atmosphere in and out again with a telescope. So you'd need a very impressive adaptive optics system to correct for that. So yeah, I would say it's probably simpler, at least for proof of principle, just to test it with having some satellite that was at a much wider orbit.
Now, speaking of traveling out into deep space, you already mentioned this a little bit. You made a beautiful video called "The Journey to the End of the Universe." And sort of at the start of that, you're talking about Alpha Centauri. So what would it take for humans or for human-like creatures to travel out to Alpha Centauri?
There's a few different ways of doing it, I suppose. One is, it depends on how fast your ship is. That's always going to be the determining factor. If we devised some interstellar propulsion system that could travel a fraction of the speed of light, then we could do it in our lifetimes, which is, I think, what people normally dream of when they think about interstellar propulsion and travel, that you could literally step onto the spacecraft, maybe a few years later you step off on Alpha Centauri B, you walk around the surface and come back and visit your family. There would be, of course, a lot of relativistic time dilation as a result of that trip. You would have aged a lot less than people back on Earth by traveling close to the speed of light for some fraction of time. The challenge of this, of course, is that we have no such propulsion system that can achieve this. So,
but you think it's possible? Like, so you have a paper called the Halo Drive, fuel-free relativistic propulsion of large masses via recycled boomerang photons. So, do you think? First of all, what is that? And second of all, how difficult are alternate propulsion systems?
Yeah. So before I took in the Halo Drive, there was an idea, because I think the Halo Drive is not going to solve this problem. I'll talk about the Halo Drive in a moment, but the Halo Drive is useful for a civilization which is a bit more advanced than us, that has spread across the stars, and is looking for a cheap highway system to get across the galaxy. For that first step, because just to context that, the Halo Drive requires a black hole, so that's why you're not going to be able to do this on the Earth right now. But there are lots of black holes in the Milky Way, so that's the good news. So we'll come to that in a moment. But if you're trying to travel to Alpha Centauri without a black hole, then the most, there are some ideas out there. There was a Project Daedalus and Project Icarus that were two projects that the British Interplanetary Society conjured up on sort of a 20, 30-year timescale. And they asked themselves, if we took existing and speculatively but realistic attempts at future technology that are emerging over the next few decades, how far could we push an interstellar travel system? And they settled on fusion drives in that. So if we had the ability to essentially either detonate, you can also imagine that kind of nuclear fission or nuclear fusion bombs going off behind the spacecraft and propelling it that way, or having some kind of successful nuclear fusion reaction